Hello everyone. Today I'm going to explain F sigma and G delta set. Now what do you mean by F sigma set? A set which is a countable union of closed set is called F sigma set. So basically what is F sigma? F sigma means countable union of closed sets. Since we know that countable union of closed set need not be closed. So F sigma set doesn't imply that the set should be closed. Right? So any set which is the countable union of closed set is called F sigma set. For example, a closed set, a countable set, any open interval, because any open interval AB, it can be expressed as, it can be written as the countable union of closed sets. Right? We can write any interval open interval AB as the union of, you consider A plus 1 by n. Similarly, consider B minus 1 by n, and when you take the union A plus 1, then A plus half, then A plus 1 by 3 and so on. So when you take the union of it, you get an open interval AB. So any open interval AB is an example for F sigma set because we can write this set as the countable union of closed sets. Now the next is the G delta set, a set which is a countable intersection of open sets is called G delta set. So a set which is countable intersection of opens is called G delta. So basically G delta and F sigma, they are complement to each other. So since we know that countable intersection of open set need not be open, right? So it means G delta set is that set which can be written as countable intersection of open. It doesn't mean that G delta is always open set, right? For example, any open set, any closed interval AB, because it can be written as countable intersection of open ones. Any closed set, a countable intersection of G delta set. So these are the example of G delta. Now each of these classes, F sigma and G delta, these are wider than the classes of open and closed because for open set there is a condition that countable intersection of open is not open, right? However, G delta, this set contains all the open intervals, it contains the closed interval also, which can be written as countable intersection of open. So these are wider ones. Similarly, we can define the term F sigma delta. F sigma delta means delta stands for intersection, sigma stands for union. So you have to take countable intersection of F sigma sets. Similarly, G delta sigma means we have to take countable union of G delta sets and so on. Now next is the result which says let E be any set, then given epsilon greater than 0, there exists an open set O containing E such that the outer measure of O is less than equal to outer measure of E plus epsilon. So corresponding to E, we always have a set O which is an open set and which covers E, which contains E, but the outer measure of O is less than or equal to outer measure of E plus epsilon. Means in outer measure of E, if we add some epsilon, now the outer measure of O is less than equal to that. Means this set is very near to E. And here the equality holds only when the measure of O, or you can say E, this is infinite. So if the measure of E is finite, we get the strict inequality. Now just see the proof of it. Assume that the outer measure of E is finite. Now why? Because if the outer measure of E is infinite and O is a superset of this E, then the outer measure of O is also infinite. So nothing to prove. Infinity is equal to infinity. So this result holds trivially whenever the outer measure of E is infinity. So we assume that the outer measure of E is finite. then there exists a countable intersection IN of open intervals such that E is contained in the union of these IN. By the definition of outer measure, we consider countable collection of open intervals such that it covers E. And now further, since the outer measure of E denotes the infimum one, but if we add some epsilon to it, now it is not infimum, so we get some summation of length of INs which are less than the outer measure of E plus epsilon. Now we put the union of these IN as O, since we know that the countable union of open is open, so therefore O set is open. So we get the set O which contains E. Now further, the outer measure of O is same as that the outer measure of the union of INs, which will be less than equal to the summation of outer measure of IN, right? Now further, we know that whenever we have an interval, its outer measure will be equal to its length. So we can replace this outer measure will be the length. Further, we can use this inequality that the summation of length is less than outer measure of E plus epsilon. So we can substitute over here and we get outer measure of O is strictly less than outer measure of E plus epsilon. And this thing we want to show. So this is the part A. Now the second part, which says that whenever we have any set, then there exists a G delta set such that it contains E and the outer measures are same, right? So corresponding to any set, we always have G delta set such that their outer measures are same, but E is contained in G. Now see the proof. In the first part, corresponding to E, we always have an open set O which contains E such that it's satisfying this inequality. So in precisely, we choose epsilon to be 1 by n, and corresponding to 1 by n, we choose an open set On which contains E. Means if you take epsilon to be 1, then there exists an open set O1 which contains E, and satisfying that the outer measure of O1 is less than equal to outer measure of E plus 1. When you take n to be 2, means epsilon to be half, then corresponding to this epsilon, we get some O2 which contains E such that the outer measure of O2 is less than equal to outer measure of E plus half, and so on. So by using part A, we get a collection of open sets On which satisfying this depending on this epsilon. Now we can write G as a countable intersection of these ONs, since we know that by definition of G delta, G is a countable intersection of open. So this G will become the G delta set such that this G contains E. Now why this G contains E? Because for each n, E is contained in On. Now if your E is contained in On for each n, then clearly it will be contained in the intersection also. So E is contained in G. Further, the outer measure of E will be less than equal to outer measure of G, because whenever A is a subset of E, B, we know that the outer measure of A is less than equal to outer measure of B. So we can apply this property over here. Further, outer measure of G will be less than equal to outer measure of On. Why? Because G is the countable intersection of On. Clearly it will be a subset of On for each n. So therefore the outer measure of this should be less than equal to the outer measure of On. So we get this. And further we can use this inequality that the outer measure of On is less than equal to outer measure of E plus 1 by n. So we can substitute over here. So we get this inequality holds for each n. So if we consider n tending to infinity, what we get, the outer measure of E is less than equal to outer measure of G is less than equal to outer measure of E. Means both are same. So this proves the result. Now the next term is Lebesgue measure. A set E is said to be Lebesgue measurable or measurable if this condition hold for each set A. So if you consider any set A, and if for this set E, this satisfying this condition that the outer measure of A is same as that outer measure of A intersection E, plus outer measure of A intersection E complement, then we call this set E to be as Lebesgue measurable. The definition of measurability says that measurable sets are those, bounded or unbounded, which split every measurable set or non-measurable set into two pieces with respect to the outer measure. So one side inequality always hold, since we know that A, we can write this set as A intersection E union A intersection E complement. Now why this? Now just see, since you can write A as A intersection R, you can put R to be E union E complement. So you can write this as A intersection E union A intersection E complement. So this is this thing, right? So what we have, the set A can be written as A intersection E union A intersection E complement, right? So this implies that the outer measure of A will be less than equal to outer measure of this plus outer measure of this, since we know that the measure satisfy subadditive property. So the union is less than equal to summation. So this inequality always hold. So if we want to prove that E set is measurable, then for any set A, we need to show that the outer measure of A is greater than or equals to outer measure of A intersection E plus outer measure of A intersection E complement, right? Because less than equal to, this inequality always hold. Now, using this, show that if E is measurable, then E complement set is also measurable. So whenever a set is measurable, its complement is also measurable. For this, we consider any set A. Since E is measurable, so it's satisfying this thing that the outer measure of A is same as that outer measure of A intersection E plus outer measure of A intersection E complement. Now further, we can replace E with as E complement complement. Now since the outer measure of A is same as that outer measure of A intersection E complement plus the outer measure of A intersection E complement complement. So again it's satisfying the equality, so this implies E complement is measurable. So whenever a set is measurable, its complement is also measurable. Similarly, one can show that the set phi and R, they are measurable. Now for phi set or R set, whatever, you can consider any set A. So outer measure of A, we want to show that it is equal to outer measure of A intersection R plus outer measure of A intersection phi. So we consider the right hand side. If we want to show that R is measurable, we take R over here and R complement, which is phi. Now since it is a subset of phi set, and we know that the outer measure of phi is 0, so we get 0 over here, and A intersection R is nothing but A, so this is equal to outer measure of A, so which is equal to the left hand side. So this implies the set R is measurable, and by using the above result, we know that whenever a set is measurable, its complement is also, right? So if R is measurable, its complement, which is phi, is also measurable. Now the next result, which says that whenever E has outer measure 0, then it is always measurable set. Moreover, every subset of E is measurable. So for this, we consider any subset A of R. We want to prove that the outer measure of A is greater than or equal to this thing. What is given to us, that the outer measure of E set is 0. If the outer measure of E set is 0, then the outer measure of A intersection E is also 0, because A intersection E is a subset of E and its measure will be less than or equal to outer measure of E. So what we have the outer measure of A intersection E is 0. So for this, we can substitute 0 in the right hand side. Also A intersection E, it's a it's a subset of A. So its measure will be less than equal to outer measure of A. So when you combine these two, what we have, the outer measure of A intersection E complement is less than equal to outer measure of A, which thing we want to prove. So which implies that E is a measurable set. Further, every subset of E has outer measure 0, and by using the above result, whenever a set has outer measure 0, it is measurable. So we get every subset of outer measure 0 is measurable. Similarly, every countable set is measurable and its measure is 0. Right? Because we know that countable set has outer measure 0, so by above result, this is measurable. Similarly, Cantor set, we know that its measure is 0, so therefore this is also measurable and every subset of it is also measurable. Now the next result which says that whenever E1 and E2 they are measurable, their union is also measurable. So for this we consider any set A, and since we know that E1 is measurable, so we get this equality that the outer measure of A is same as that outer measure of A intersection E1 plus outer measure of A intersection E1 complement. Further, in E1 complement, over this set, we can consider this to be any set A, and for this any set A, since E2 is measurable, so this should be equal to the outer measure of this intersection E2 complement. Right. Now we can combine first two one. Now just see how. Since what is E1 union E2? E1 union E2 is E1, its union with E2 minus E1. E2 minus E1 is nothing, E2 intersection E1 complement. Right? So when you take A intersection, you get this thing. So the outer measure of this will be less than equal to this plus this. So we can replace this thing with outer measure of A intersection E1 union E2. And this side we get outer measure of A intersection E1 union E2 complement. So for any set A, outer measure of A is same as that outer measure of A intersection E1 union E2 plus outer measure of A intersection E1 union E2 complement, which implies that E1 union E2 is a measurable set.